So I'm recording it now. Yeah.
Okay.
Okay.
Yeah.
So yeah, that makes sense for that. And then I assume like when you're doing 30 for here.
This is a pre-PCA analysis that needs to be done, because when you do MSSA, there is a possibility that you end up with a very large matrix, and MATLAB may not handle that. For that,
Right.
you need to have a dimension reduction at the first step. So
Right.
this step basically reduces the dimension to 30. I mean, instead of so many grid points. So what basically it does is once you do PC analysis, it first of the few eigen modes in the PC analysis captures most of the variance. If you sort out the modes into their decreasing order of variance explained.
Right.
As I said, 30 will be a good choice with the trim data. But if you're working with some other data, just look into how much variance the first 10 or first 20 modes are explaining. I retained around 85 to 90% of the data because I wanted to work with most of the data, and the rest of the 10% or 15%, those are basically noise. I mean, you can anyway remove that.
Okay.
So yes.
What we are looking actually is we want to retain as much as data as possible.
Right. Yes.
So you are saying we have, let us say we want to use, how many days window we need to use here? 60 days you are saying?
Yeah.
Australian monsoon, if you we can start with 60, and if 60 is not working, then you can reduce or you can increase.
What do you mean by not working? That means we are not getting what?
Not many significant modes or oscillatory modes. Just you have to be sure that you get an oscillatory mode for each year, and then for at least for
okay. So let us. So his data, it is for the Australian data, and we have saved for from onset date. I think 60 days before and after we have saved. Correct,
Yeah.
John? Okay. So he has this data in the yearly file, and the yearly file name is D2014. And
so how long is this data set? I mean, the DAT
1900 to 2015, so it's 115.
No, each of these files is this daily data, right?
Yes.
And how long are each of these data sets?
How many day in the data?
How many days?
There's 196 days or 197 if it's a leap year.
So for the leap year, 197. Yeah. So
okay. That should work fine. I mean, with 60, I mean, just make sure that if the length of the data set is let's say n, and if you have a m window length, then n by m, that ratio should be at least greater than 3. You should
greater than 3, you are saying?
Yes.
Okay, so if we choose 60,
yeah,
that's greater than 3. Yeah.
So it is 180, so data is more than that.
Right.
So we can choose 60 here, and then we can move further.
Right. Yes.
Choose and run. So let us say you can put a command whos, WHOS, to see whether the data is loaded correctly. Enter. So we have 196 by 53793. So these are the number of grid points, which is 601 by 201, right?
Yeah.
Okay.
Okay.
So we have arranged the data in this format: time multiplied by the space.
Right. Okay.
Okay. And if you want to check, this data do not have any undef values, or this data also don't have any nan values, and those things can be checked by max and min value of this x.
Right.
Can you do max of x? Okay, min of x. I mean, just we are recording, that's why I'm saying and repeating these words, so that
you can check with ISNAN.
Okay, is nan?
Is nan, yeah.
ISNAN. NAN. No.
It's ISNAN.
Is a command.
Like that?
Yeah. Bracket. No. Is nan bracket x.
Give the matrix. bracket X.
Oh, and then I have to do that.
Yes.
Okay. So
It's
I mean,
going to print out. I mean, if all of them are 0, then it is. I
yeah,
mean,
we
you
cannot
can.
see actually whether it is 0 or
Yeah,
1.
yeah, yeah. You have to just modify the command. It's just
Okay, can
isnun
you
is the
close
command
it?
with that. If there is a
Control
true
C.
value, then that should be 1. Otherwise, it should be 0. Just put a max of ISNN. Yeah.
It should come out as 0.
Then again,
Or
max of ISNN.
Yeah.
Yeah. It should be. It's already. You have seen that max and min are already.
Yeah.
Yeah, it's logical. It's 0. Yeah.
so we have the data now. So the second command we can type now. And we have prepared a script, correct? Can you open our script in the another terminal?
Yeah.
Read data.m, I think.
Yeah, that's what it was.
That was there in the another terminal. If you see.
Oh yeah, I guess I can go in there.
So you no need
Yeah,
to
let's
add
do
another. So you just open here, or you can do VI or anyway, whatever it is. So what we have done is just ll.dat has all the data
Mm-hmm.
we are storing in nm variable, and then
Okay.
for each. So I have defined for I equal to 1 colon 1 and percentage. That means we are just taking a single file,
Right.
and then file name it read, and then it open the file name. It's a binary file, and it open f read. This is the size which we store, and then we
Yeah.
define p. We can multiply it by 60. You mentioned float. Okay.
Yeah, it needs to be float, otherwise it
Okay.
defaults to characters.
Then we define p equal to precip pre
Prep
x
CA.
comma 60. You mentioned, right? We can change it to 60.
Oh no, the 60 was here.
That's 60 is fine.
What about x comma 30? What it is?
Oh, that's a pre-PC analysis. You want to retain 30 modes out of these 190, out of these 53,793 channels.
Yeah, that's the data
So
we're looking
Retain all
at.
these
how much is
pixels.
recommended to keep?
I mean, it depends upon the user. I mean, if you are looking into very prominent signals like ENSO, then 10, I mean, is fine. But for precipitation with trim, very noisy data set like rainfall with very high resolution data like trim, I prefer to retain most of the uh,
Most
variability.
of the right.
Yeah, so that's why I took 30.
So most
Right.
of the means why 30 most in the most it should be 53,793, correct?
No, you want to reduce the dimension. Right? You want to reduce the size of the matrix with retaining all the I mean most of the information you want to keep.
Okay,
So
so most of
80 to 90% of the variability is sufficient enough to diagnose any interseasonal variability. So
okay
30 actually captures most of it. I mean,
okay
if you take 30 with trim data, that gives basically 80 to 98, almost 85 to 90% of the variability. So that's
okay
why I kept 30 as
okay, let us run this command and
yeah.
we'll see what it will show.
Yeah, it will show the amount of variability explained. Yeah, so you can see, just go to the top of the.
So these are 30. Oh,
What are those? Why so many?
can you
Yeah,
see
yeah, yeah,
size of p? Hmm.
yeah, yeah. This is the column. Only one column should come. Yeah.
So what are the
I
below?
think. Yeah, I think you might have. Did you open the pre-PCF file or did I change something there? It should come only that first column and 84%, 84.668851.
Yeah.
That's the percentage of variability explained by these 30 modes.
Hmm.
Right.
And these 30 values above this is basically the eigenvalues or the percentage variance explained by these eigenvalues.
Okay, so 30 become like if we see it is
So
very
as
small
you can
number.
see, I mean, just you can just scroll up that command. Yeah, as you can see, the first column. Yeah, just go above. Yeah. Why there are
Right
so
here.
many?
Yeah.
Yeah. Why this is more than 30? or as
Yeah,
you can
and
see, I
it's
mean,
definitely more than 30.
yeah, I mean,
Can you check the
I think
size of P? SIZE of P? Yeah, it is not visible. You have to move. Yeah, size of P, capital P.
yeah, yeah, it's
I think it
30.
is 196 and the 30
Yeah,
columns.
yeah. Can you, John? Can you type this previous command with a semicolon at the end of it?
This one?
Yeah, this one with the
Yeah.
yeah, yeah. This actually,
This
196.
is what you, right.
yeah. So this is basically all the eigen components, and 84.6% is the variance explained by the 30 modes. And you can see the eigen value percentage variance explained by these eigen values. And if you scroll above, scroll up, and you can see that after 20 or 30th eigenvalue, the variance explained by the eigenmodes basically is very less. I mean, zero point 0.4 or zero point 0.5.
Yeah,
If
basically
you
nothing.
include 5 more or remove 5 more within, I mean, let's say if you take 25 or 35, it is not going to change much.
I have
Right.
one question here. Like the size of P is 196 by 30. So what we are doing here is we are doing over time, correct, rather than space.
Right.
So is it recommended, or we have to go other way? Like we have to transpose our X and then we have to do this one.
What in the README file? What have I written? Is it times? I think it is times cross space. Can you scroll
Yeah.
up?
And we
Can
have,
you scroll up?
okay.
Yeah.
So is it time cross space?
Yeah. Yeah. Yeah.
Okay, then we have arranged the data according to this file only.
Right. Right. This looks fine.
Okay, then go to the next step. So you can choose from our code MC equal to MSSA MC. No, no, okay.
Yeah,
So what?
I was testing this out earlier.
Yeah. Just put a semicolon after that. Otherwise, it will show all the.
So what are
Right.
these 60 and 1000 and reds and 25s? Can you say again?
Yes. So MSSA MC is the function that actually will operate on P matrix with 60. That's this is basically the main major function in this total programming folder. And 60 is the window length that you are using.
So
1000 is the number of surrogates, the AR1, the red noise surrogates you are using for the significance testing.
okay, so okay, these are the 1000 is the random experiment, like
So this is basically significance for the significance test. So you can put 2000, 2500. The
I
more you
understand
are
it.
putting, the more number of red noise surrogates will create, and it will do the significance testing. You can put 100 as well. I mean,
I
1000 is
understand
a
it. Yeah.
reasonable number.
Okay.
Then
So and what is this
REDS.
true and false?
Yes, I will come to that. So, John, can you go to the README file? Oh yeah, yeah. So this is basically the method is REDS, that's reduced covariance matrix approach. Okay, so John, if you remember, I mean, we talked in the last when we met. I talked about there are several methods that can be used for MSSA. One is the Broomhead King approach, and then there is the Toeplitz matrix approach, and then there is reduced covariance matrix approach. So the first two methods, they basically diagonalize a very large matrix. So if you have, let's say, M window length of 60, and you have L channels, so that's number of channels is 30 now. So in the first two methods, it will diagonalize a matrix of size L cross M. Okay, So that's a very L cross L into LM cross LM. So that's a very large matrix. So for example, if you have 60 window length with 30 of your channels, so that's basically 30 into 60, that's
1800.
1800 cross 1800. So that's a very large matrix that is going to be diagonalized. What happens in the reduced covariance matrix is it will create another matrix, a covariance matrix of n prime dimension. So that's n prime is n minus m plus 1. So that's basically if you have 196 time step, and then if you have a window length of 60, so that will create a matrix of 196 minus 60 plus 1. So that's basically 134 or 137.
Right.
And then it is going to diagonalize 137 cross 137 matrix. So that's a much smaller matrix than the earlier one.
Okay. So we can now go.
But you are going to get the same eigenvalues in this approach as you are going to get in the other two methods.
Okay.
Okay. So that's this is the main idea of using reduced covariance matrix.
Okay.
And the rotate EOF is you are going to rotate the EOFs basically to their. So that's the rotate EOF is basically a varimax rotation. You want to just rotate. So basically, what these methods do is it basically captures the dimension along which the data explains its most of its variability. In some cases, what happens is you do not get the actual direction upon which this variance is explained. You just rotate the axis so that you get more meaningful patterns out of it. So that's basically does some visual. I mean, that's basically for just for visualizing the patterns more clearly. You just rotate the EOFs accordingly. So you can do it, or you can just ignore this part. If you do it, if you put 0, you will not rotate any of these EOFs, and it will retain all the EOFs as it was for MSSA. And you can just choose 10 or 25 or 15 first 15 eigenvalues just to rotate them and then see what happens. So this does not make any very big difference. You can either choose it, or I mean, you can just ignore that.
Right.
Yeah. But for the timing, if you are, I mean, you don't have to go beyond 25, because below 25, if you're dealing with some eigenvalues, then they're very small. They have a very small eigenvalue, and they do not explain very much of the variability in the data. So it's better to stick within 10, maybe 15. That should be fine.
Okay.
And the last part, if you can put true or false, that's basically the plotting the eigen spectrum. If you put true, then that will plot the eigenspectrum. If you put false, that will just suppress that command.
Yeah, you can submit this now.
Yeah.
And another question is, after this command, there is a file a equal to mc.af and e equal to mc.ef. What are these two files?
Yeah, I'll come to that. Yeah.
Okay.
Just let me see what it shows.
Disabled some advanced graphics. So since we put true there,
oh, it's fine. It's fine.
Plotting
it's
it.
just, yeah, since he has put a true in the last, yeah.
So it shows few numbers. Okay. Eigenspectrum with MC testing against signal. So what this figure says?
Yeah. So first, I have to say that just before going into the figure, there are some numbers that popped up in your command window.
Yes.
So there's 1, 2, 3, 5, 13, and 14, the first column. So that basically says these are the indices of these modes that are significant. Okay,
right.
So mode 1 is significant, mode 2 is significant, mode 3, 4, 5, these are significant. The next column, 142.57, 110.88, these columns says these are the periodicities associated with this mode. Okay.
Okay.
These periodicities are actually calculated using a Fourier decomposition. And just where the peak is, if you just take the PC or the UF of these modes and then do a Fourier spectra, and then this basically finds out where the Fourier peak is, and then it just prints the value.
Right.
Okay. The third column is the eigenvalue associated with this mode. So as you can see, the mode 1 will have the maximum eigenvalue, mode 2 will have eigenvalue less than that, and so on and so forth.
Right.
Okay. Now, if you have understood this command window, this prompt, this printing, then if you go to the figure now, so the error bars that basically come from the 1000 red noise surrogates.
Right.
If any mode that lies above or below this error bars, they're significant. So this is not in the convention. I mean, conventionally, what we show, I mean, in our regular climate plots, if the error bar should be, I mean, cover the actual value. But here we are saying that this error bar is basically the AR1, the red noise spectrum.
So it is the tail of the normal distribution.
Not
5%
normal
rejection area in the normal distribution, we say normally.
Yeah,
So
if you, I mean, there's a nice analogy. I mean, this is basically the 5%. This is basically the 95% of this error bar is basically the 95% of spread of this
significant values, and if it is falling outside the these lines, then it become a 5. You mentioned 95%, right? So 5%.
Yeah, this is 95%. The default is 95%. So
Right.
first two actually shows that they are significant. So they are lying above the error bar, and hence they are significant.
Right.
Then there are two in around 0.808 frequency, right? So
Yes.
they are significant.
Okay. So which mode we need to focus on them now? Like there are
now there is a very interesting fact. I mean, with the window length of 60, I wouldn't expect some 110 and 142 these modes coming out to be significant. So the first two modes, they're significant. That is surprising. That looks surprising. And I can see there are two modes significant at 0.08 frequency. Now, in the print, I cannot see the other one. That's only one with, oh, I'm sorry, that's mode 4 and 5.
Yeah.
So this is the one with 45-day periodicity. So if you just ignore the first two, then the third mode explains 45-day periodicity, and fourth and fifth explains the 12-day periodicity. Now it is fine to have only one mode. I mean, usually MSSA captures oscillations usually by two modes, a pair of mode. But in this case, the third mode explains 45-day significant mode, but it has only one mode. It can happen that one mode is just scrambled across the eigenspectrum, and it is kind of contaminated by some other modes. So it is not popping out in the analysis. But if you just plot the phase composite or the reconstruction of this mode 3, you can see the propagation characteristics. But what is surprising is these first two modes. I mean, 110 and 142. I didn't expect this kind of modes coming out to be significant. The rest of it is just straightforward. 45-day, that's a low frequency ISO. 12-day, 11-day, these are high frequency
ones.
Yeah.
Right.
These are very typical with monsoon, Indian monsoon.
But this is Australian monsoon during the winter. I mean, their summertime.
Right. But They have low frequency and high frequency ISOs as far as no, but these first two modes are, how did you uh, treat the data before you did the MS PPCA? Did
Like
you
Uh,
I can
remove
answer.
the climatology?
yeah.
Okay, and how did you define the climatology?
So I had previously actually done a daily climatology before, so I basically just took the what I'd already previously calculated and subtracted it from each of the daily data at each grid point.
Okay, so that's basically calendar day mean.
Yeah, daily climatology or all 100 years on a 1st January are added.
Yeah.
So
Yeah,
100, so and then subtracted from the that day. So it become anomaly.
right. And did you do some normalization of the data? I mean, is it,
We did not.
could you just try by normalizing the data first
Yeah,
and
we,
then,
so by normalizing
I mean,
can,
it should have a zero mean and one standard deviation.
uh, but uh, but that has to be done with the actual data like we have in this stat file. We have
Yeah, yeah,
only,
I mean, just, I mean, you can do it by one command. It's just, I can
so
just,
so this
if,
is
if,
anomaly, right?
if X is the data, then if X minus mean of X by STD of X.
Yeah, that's the problem, right? Oh, okay. We need to x minus mu. So x minus mu is already been printed. So we have to
Yeah,
get the
for
standard
each of
deviation.
these grid points, for each of these grid points,
No, no,
you have to
that
do it.
has to be done with the Fortran code we have there
Oh, okay.
because we
No,
already have the anomaly here. So at
yeah,
present
yeah,
we
we have
have x
anomaly.
minus mu. So we have not divided this by sigma, and that
No, I'm
sigma has
saying
to
with
be
the anomaly
computed
data.
for each grid point.
No, no, I'm saying with the anomaly data, you can do it, right? I mean, you can just,
We need to divide it by sigma.
yeah, yeah, sigma can be found out by standard deviation of X, STD of X.
No, we cannot use that.
Why?
Because standard deviation sigma will be different at each different grid points, right?
Yeah, yeah, I'm saying for each grid point, it should be different. I
So
mean,
at present in the MATLAB code we don't have in, we have in the Fortran code. So if you want, we can generate the new files.
no, no, no.
Yeah.
Just, John, can you just,
Yeah.
all I'm saying is just write just 3 lines for I equal to 1 to length of X.
No.
X is the file, right?
Yeah, can you do size of x
You
first?
want me to do size of us?
Yeah,
Yeah.
I'm saying like size of x has
Yeah. So,
these many
yeah,
grid points.
yeah.
Now the problem is how you will get x.
No, it's so you can just print, let's say, N1 is equal to size of X.
Sorry, say again.
Yeah, N1, just write any variable N1 equal to size of X. Yeah, just, yeah, then enter. So N1 1 comma 2, just see what it shows. N1 bracket 1 comma 2.
It will be that number.
Yeah, yeah. So now you can just let's say capital N is equal to N1 1 comma 2. Define N is equal to, yeah. So now you can just write a for loop for I equal to 1 to capital N. Yeah,
Okay.
yeah. Then go. Let's say yi, capital yi, y of I, y bracket I. No, you have to give x colon comma I. Yeah, is equal to x colon comma I.
Bracket.
X Yeah, in the bracket, minus mean of x,
X,
uh, x colon comma I. Yeah, then put all this from beginning just after the equal sign to the end of it.
but mean of you are doing
Yeah, temporal mean.
okay,
By then divide it by standard deviation of x colon comma I.
but this is already an anomaly.
No, this is just normalizing the data. Anomaly is you have removed the climatology, right?
Yeah,
So that doesn't have basically the zero mean.
but
Then
I understand you are normalizing this data only, right? You are not normalizing the original data,
no, 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 not the original data.
only this X variable.
Yeah, just the x variable, what I'm going to feed into MSSA. Then you can just put a semicolon and then end it.
And
And then
enter.
let's see what it shows.
Size of Y, and then print Y enter.
Why is it 196 cross 1? Oh, is there a mistake there?
Yeah, it will be.
Why it's only one column?
Yeah.
I will suggest you to write these commands in the left window where we have the subroutine. Yeah, just copy paste command before after like X,
Mm,
Oh
yeah,
yeah, like right here.
enter here. Yeah, add all those commands here.
yeah, that should be fine.
Do you know that 196 is starting from its onset? I think how many days before and after?
It's about how many days is it again? I think it's
99 100 is 200, so it is not even 100. 98 days from onset.
yeah, something like that. I forget exactly what I used. I think I did like a month and a half. I think it was 45 days on either side. Something like that. I can't remember exactly.
Okay. Or what do you say, Nirupam? We normalize the original data itself.
No, no. I mean, the normalization should be done before the send the code, the data to MSSA. It should be centered and normalized.
But is it not like last time you mentioned that Recip PCA will normalize it inside?
No, pre PCA doesn't normalize it the data. I mean, normalizing is not very strict thing to do here, but I'm just checking if it removes the 142 day that mode.
Okay.
I have not done this normalization for my study. I mean, this is not a very strict requirement. If you are doing anomaly, that is fine enough with climate data.
Right.
Now, why? Where is that? Why is
Because
that?
the size of mean has to be squeezed, and the standard deviation of
Oh yeah,
output.
yeah. It should be squeezed. Yeah, yeah,
So you can type
yeah,
before mean. You can type
yeah. It should be
squeeze
squeezed.
before mean. You can type, yeah, before mean. Yeah, here after minus squeeze SQUZE. SQUEEZE.
Like that.
Squeeze.
Eh,
Yeah.
no. SQUEEZE.
Oh, okay.
I hope it is correct.
Yeah. Let's see.
And bracket, and then do for same thing for standard
Standard
deviation.
deviation as well. Yes. Well, that's why it gave only one column.
And now
It should work.
comment all the below part, or till A, like leave these two and A,
Oh, down
E,
here.
yeah, comment all those. A,
What's,
E, comment
is
these,
it
percentage.
what? Oh, percentage is the MATLAB one. I forget which one's
Yeah, go down, percent, go down, percent, and so leave end. Yeah, save this code and run this one. I hope the data is in this directory.
Yeah.
Okay, run this code now.
Well, should we go? Do we want to go through all the years, or do we just want to do 1 year to
It
test?
will
Just
do
one
only
year,
one.
Just one. Just I
It
want to
will,
check whether this 142 code this day is coming or not.
yeah, you
Okay.
can run it. It will do only one because we have put the command one only there.
Okay.
Run this code.
Now, are you going to use the same year that you were using last time? I mean,
No, this will be a different year because
And also you have to change those numbers, reds, comma 25, comma true, right?
yeah.
It will be a different year, but it is fine. Let us see what it will generate. You run this code.
no. Actually, I wanted to see with the same year.
With this exact year.
Yeah. So that I don't get.
Then in FID, uh, copy this line and comment one and paste the year. Oh, sorry, not year side. I think it is F read we have to define.
I just
Or,
changed the file name just to the same year.
or you define I. What is the number of that I?
I just did the last one, so 115.
So you can write 1 colon, okay, I equal to 150 colon 150. Oh, 115. Okay, it is fine. Now run it.
Okay. Should I run it? Which window should I run it in? Should I
Run
just
this.
create a new
Yeah, in
window?
the right terminal you can run.
Yeah, the right. Yeah.
Can I run it in here? Oh, I guess I can. Yeah.
Run, 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 space, this script name. So 2014, right? Okay, so it is the same thing.
That's fine. 84.668. That was the number we got last
That's
time.
what we had before. Yeah.
Yeah. Let's see.
And you can minimize your email because everything is recorded.
Yeah.
Background email. I mean, just, but it is fine now. At present, it is okay. Let it come.
No, it's
So
again showing.
who are there? So are we doing normalization? Can you check size of Y on the right terminal? Size of
No,
Y?
actually, you have to pre-PCA. That's using the X matrix. You have to change it to Y.
Oh, I think, yeah. Okay. In the right code, just rename X to Y in the line of pre-PCA.
Yeah.
Which one?
Yeah. Y
here. Oh, yeah.
That should be Y.
And run it again.
Okay, so there is a
Can you check size of Y?
Size of Y, yes.
Size of Y. It's a problem.
Can you do a squeeze of X as well? I mean, in that Y equal to that matrix.
No.
Yeah.
No, we don't have to put squeeze here.
I don't know. Let's see. I mean, can you just take all
I
these
think
three lines?
the problem is when we put the squeeze, it reduces the dimension. But when we are subtracting, it is not taking it as a column wise. Like it is not subtracting all the columns of.
Okay, let's see. Just copy
Let,
these 3 lines and paste here in the command window, and then see what it looks. From end to for. I mean, the 3 lines.
Oh, right here.
Yeah,
Yeah.
yeah.
Oops, that's not what I want to do.
Okay,
there are so many brackets.
it's again 196 cross 1.
It should be 1 to so many times. That means we are not. I mean this. I mean this can be corrected, but I have to do it. You want me to write the code here?
Yeah, this is a very trivial thing to do, but
Yeah.
there's something going on that's
Confusing.
yeah.
So what I can do?
Squeeze of x. I mean, John, just try to let's see each of these parts. Can you just print a squeeze of x? That's the first part.
Oh, so you want to just do a squeeze of x?
X bracket colon comma 1. Let's say.
Like that?
Yeah, let's see what's that's a 196.
Yeah.
Yeah, and then squeeze of mean of the next part. So everything is 196, I think. Okay. Okay, that should be one number, and then somehow the standard deviation, that should be again another number. Somehow the code is stopping at. Yeah, that's fine. These are fine, but why the code is not running for the all
Because we
the.
have to multiply it by a vector. I mean, this is a number. You multiply by vector, then only subtraction can be possible. I'll do in my account. Let me prepare the account first.
If you subtract a number from a matrix or a vector, all the elements are subtracted. The problem,
Yeah.
I think, is happening. The loop is not running through
All
all
53,793.
53,000 values. It's just stopping after 1.
I'll correct it. It is not a big issue, but since
Yeah.
John is a newcomer, we need to
That's
like
fine.
he will be able to correct, but it
Yeah, that's
may
fine.
take time.
This is just somewhere you have to put some bracket, and then it will be fine.
So what is this code name you're running?
The one that I just ran is readdat.m.
Read that.m. Okay.
Yeah.
So let me share my screen and I'll do from here. 1 second, let me copy also your code. Copy. allow me to share.
Okay. You should be able to now.
Yeah.
So let me correct this one. I'm just running to.
Oh, I'm sorry. I just this is a wrong command here. For I equal to 1 colon n, it should be colon n, not comma.
Oh yeah.
Yeah, I got confused. I mean, the
Yeah,
command
I did
is
not even
common
saw
in
that. Yeah.
NCL. Yeah, and I
Fine.
used NCL command in some MATLAB. This happens very frequently.
Right.
Yeah, MSSA. What is that directory? Data, right? And 2014, right?
Yeah.
No. Oh, these are very big files. Sorry, give me a second. I did.
Are you copying all the files somewhere?
Yeah, he's copying the files into a directory that he has.
Yeah. So this is going to take a long time.
Not long. Not long. So let us see the code here. So this is the code we have. So 196 plot. And this has been done. So in the meantime, you can mention what are A and E.
Yeah,
MC.AF.
A is the the A is the PC and E are the spacetime EOFs.
So how we have created these files?
So these are basically in the structures. So once you get MC is defines MC is structure that contains some of this data. So in the MC you get AFs. AF, these are the space-time PCs that are located within the structures, and EFs are the space-time EOFs that are located in the structure. So you have to extract those data from the structure before you can work with them. So the first two steps, A and E, are basically extracting the actual matrix from the structure. Okay. And once you have the PC,
This is same for everything, every type of data.
yes.
So you mentioned structure, but I don't understand it completely. What structure you mentioned, but
So that's basically, I mean, you cannot see the matrix in your workspace. MC will be it will show in the matrix in the command window or the workspace as a structure, not a data.
now
So
the eigenvalues has changed by normalizing.
Right, right.
Okay.
Yeah, so now what it shows is 47-day 47-day oscillation is there, so that's fine. But
It's
these
also there.
these two are also there. So
And now the negative part is not there, but it all are like first and second mode, and then you can say fourth and fourth mode, and then this
so
is
that's the third mode. That's the yeah, that's third 47-day periodicity, and then you have 12-day periodic 2
oh,
mode.
so these are the 1, 2, 3, 20, 11, 10. What are these numbers?
These are the indices of these modes. I mean, first mode, second mode, third mode, 20th mode, 11th mode.
Where is the 20th mode? Okay,
20th mode could be anywhere. I mean, somewhere in the middle of. In 20th mode is somewhere just if you look at the x-axis, just after
3,100.
0.04. Yeah,
Oh, okay. So this is based on y-axis the eigenvalues,
yeah. Y-axis is the eigenvalues, the values, and x-axis is the frequency.
and what are the significant modes? This is first, second, and then
Yeah,
another dot, and these dots, right?
yeah. These dots, and then there is one just after 0.04. Yeah,
This one.
yeah. This one is significant. Appears to be significant because 34 could be somewhere around there. No, 34 is somewhere between 0.02 and 0.4. 0.04 here. Yeah,
Here,
that
okay.
one is significant. That is above the error bar.
Right.
How did you know that this one?
So if you look into the periodicity, so it's 34.41 days,
Okay.
and that is significant. And 34.41 is somewhere between 0.0 and 0.04. So that's frequency I mean, just 1 by periodicity, right? If you divide 1 by 34.41, that
Okay.
should the x-axis. I mean, that's how it is plotted. And it is significant, meaning it is the error, the eigenvalues are above the error bars.
But yeah, I understand if it is above, it is a significant. But you were looking some data and then saying it is significant by without looking the chart, correct?
No, I can look at the chart as well.
Okay. Okay. Then up to this part is covered.
Yeah.
So we can say that it has 166 days of oscillations, 99 days of oscillations.
Yes. Now, why I was looking into this centered data? That's because I was surprised by looking into 166 and previously 142 days of these oscillations.
Do you want to check another years?
Yeah, that should be fine. I mean, we can check another year. Let's see what it shows.
So let us say first year we can check.
Yeah. See, so the first 30 eigenvalues explain almost 93% of the total variability.
And then let us remove these also to just for run.
Yeah, this is even more cleaner signals you can expect from this year.
Yeah.
So there's a very prominent low frequency isolation with 24 days oscillation and a very prominent high frequency oscillation with a 12-day periodicity.
Right.
Yeah. Now, the interesting thing is in both of these years, you are getting a oscillation. I mean, I'm not saying an oscillation, but a significant mode with a periodicity of more than 100 days.
Right.
Okay, now why is that coming? I would say that that is because within that particular year, that could be related to some trend or some uh, I mean anything beyond intraseasonal oscillation and below the mean. So what I'm trying to say is that could be attributed to some trend for that particular year,
Right.
and that may not be an oscillation, because with a window length of 60, you do not expect an oscillation to be diagnosed of 124 days periodicity.
Right.
Now, these kind of things can happen when you have a strong trend in the data that was not removed by the removing the anomaly, and that is what happening here.
Okay, so what are these windows here?
Yeah, so the A, E, and 30 and 4. As you can see, I mean, in the README file, I mean, these A and E are already you have calculated from MC. Okay, and then numpc, um, this 30 is the number of PCs that he used for the pre-PC analysis. That should be consistent. You use 30 PCA for the pre-PC analysis, so you put 30 here. Okay, and for index, you write what are the modes you want for the reconstruction.
So
So let's say
what are the modes means you want 4 modes?
no, you have to write the indices. I mean, I mean, let's say you write third bracket, uh, close brackets. I mean, 3 and 4.
Big brackets like that.
Yeah, yeah.
So what?
3, 4. Yes.
So why
And
3?
because you can see from the chart that 23 and third and fourth mode, they show periodicity almost equal. I mean, they are basically equal, and they have almost equal eigenvalues.
And then we
Yeah.
also want 8 and 7.
You can do it separately, but not together. I mean, if you do it together, then that will be a combined oscillation. But you want to look into low frequency ISO separately than the high frequency ISO. So you want to use, or you want to look into the low frequency ISO first.
Okay, and then so we have to maintain the 30 everywhere.
Yes, whatever it is. I mean, if it is 15 in the top part, then you should write 15 here.
And
Because
what
it is
about
again
RC?
putting, I mean, once your MSSA is done, you are putting back all the data into their respective points when you want to plot. So that is what it is doing. I mean, you are getting this reconstruction back to their physical space. So these are the 2 steps that are being done. So you have to be consistent with the earlier steps.
And what about this RC? It should be 8 mode or 2? How many modes?
If
You
you
want
say
8 composite?
yeah, 8 is a very popular number of composites that are used. So
Okay, so we are running with that.
yeah.
So last time it showed us error. So once we get phase composite, do you have a MATLAB code just to display this phase composite?
Now, once I had phase composite, I took all the data to NCL and plotted it, because it's just spatial plots, and I didn't do spatial plots in MATLAB. MATLAB is
Right.
not very friendly
Good for
software
that.
for spatial plots.
Yeah.
You can do it in grads. I mean, this is basically the number of grid points into 8.
Okay, so this part is done. So
Now
MATLAB
remember,
has
I mean,
done.
you will
So do
get
we need to save this variable?
yes, phase composite. It's already saved in the workspace.
I don't see it.
It's in the workspace, not in the
It's in the workspace.
MATLAB workspace. So
MATLAB workspace, yes.
you'd have to then save that data into a file.
Oh, okay.
Yeah,
So
you can write DLM write or something like that.
Yeah.
save phase dot composite, right?
Yeah, but you need to do that before. Yeah,
Yes.
something like that. Yeah.
Correct. Will it save?
If you say phase composite.mat, then it will save a mat file.
So
Can you work with a mat file in other
format you
softwares?
want.
Probably just a DAT file, just .dat.
Yeah, you can save by, I mean, you can write it by DLM write. Which software are you going to use for plotting?
I use grads usually.
Can you use it .dat files?
Yeah, if you write the correct
Yes, then you can write DLM write,
GTL file.
DLM write. Yeah, then phase composite.
File name.
Or no, the data itself, phase composite.
Just the phase composite. Then you,
no, without the DAT, just the actual variable.
Yeah. And then yeah, the delimiter, and then that should be fine.
File name.
Yeah, just help DLM right.
I'll check. Yeah, I understand.
Forgot the L.
Can you see what the dimensions of phase composites are? I use this MSSA code.
This is 8 by
yeah.
So
this is 8 phase composites. The 8 is the number of phases, and this is the number of space grid points. So now when you plot, you have to make sure that
I put the data, the gridded data back where
to the
it came
grid.
from.
Yeah, you're right. Yeah.
Do you have a NCL prepared script so that we just directly visualize it, phase composite?
Oh, yeah. I have to check.
Just we want to plot rather than making.
Well, the problem is that his NCL file is going to produce a map of India, whereas we want a map of Australia.
But he will change the dimension. Like we
that
can
is
change
fine. But NCL, actually, I have all the files, but they're not pretty user friendly. That's the problem.
Right.
How did you convert the data, the Latlon data, into this 53,000 this file? Did you use?
Yeah. So what I ended up doing was I used a Fortran code, and basically I had a mask that I'd created previously. So basically I set all the oceanic values, which were the bad values, to a negative number. Then basically I told the map, or the Fortran code basically just said, if the number's negative, just ignore it. And
oh, okay. This is going to create a problem now. Now, I faced a similar problem with the IMD data in over India. So what you can do is you can, let's see, you can just use, you have the Australian data, right? I mean, wherever the values are missing, there's a NaN value or some UNDEF value, right?
There's not actually. The Australian data is strange in the fact that there is actually a value at every single grid point, but the values over the water are less reliable. So I chose to get rid of them.
Okay. So once you got rid of them, you can write that file. I mean, you can write them as over the oceanic values as NaN, or a very high value or a very low value, negative values. Okay. Now, once that is done, you just write that particular file for one day. Then you get a map for one day, so that the land data will have some reasonable values, and the oceanic data will have some high or very low values.
Right.
Now save that file. Now, with the MATLAB code, you just copy that data into your MATLAB code, and wherever these data, the land data is, you just put those these particular phase composite matrices into those
spots.
Yeah, so that's kind of what I did with the IMD data. With stream data, I had not any problem, because stream is a very continuous data, and over ocean, over land. So you just I just use the resave function.
So I was able to save in that. Now the question is, we have to read this with the Fortran code and the size. PC. minus L. So the size is a problem. Oh, okay. Sorry.
Can it be by 8?
That's fine. The size
Actually,
is not very big.
no. Problem is what it is saving, because the size should be this exact numbers.
No, the size is basically it is MB or GB, right? This is in
So
bytes.
this is a sequential file. I have to check whether it is saving a sequential file or some other data format. Is it a way to save in netcdf file?
Yeah, you can see NC create.
Okay, let me save it in netcdf. So NC
But
create, right?
yeah, the problem will be the same. You have to rearrange the data into your land grid points.
Okay,
Yeah.
that part will do. I'll do. That code has to be like, I will write that code and then yeah. So do you expect that these phase composite will come out as a fair? I mean, because you mentioned that these are the false mode, right? For the
Uh,
3 and
these are
4.
not false. I mean, I would very like to see what are the phase composite diagrams, or at least the PC. I mean, the reconstruction of these first 124-day mode. But definitely the modes 3 and 4 and 5 and 7 for this particular year are explaining ISO. I mean, that is pretty much sure about that.
Right.
So if I provide you this data, will it be
Yeah.
possible for you to make it a plot? If you have
So
a,
it'd need to
I
be
need
rearranged
I
back
need
into
the
the.
rearranging file for that. I mean, I need where the data is taken from.
Hmm.
If
I
I have that,
understand. Yeah, yes, those has to be rearranged.
right.
But in our rearrangement, we did not remove any grid point, right? Or we removed the ocean points.
Yeah.
Okay, all those code has to be prepared. So what we can do, we can prepare a code which will rearrange this, and then we plot it, and then we can discuss further with you. What do you say? Tomorrow?
Yeah, sounds good.
You have time
Tomorrow,
tomorrow?
uh,
Like half an hour or so?
in the morning.
Anytime?
Yeah,
Yeah,
morning will be fine because I have something in the afternoon.
no problem. What time tomorrow morning?
We
Morning.
just plot and we'll see, because everything will be ready
Yeah,
in front
you
of you.
just see how the plot is coming. You can just if you are getting the plot, then you can send me through email.
Yeah, that's
And
true. I can. Yeah.
yeah,
Sure. And then we can
uh,
also discuss what are the points, and then we can discuss the points in
right,
your publications, that these are the phase composites,
right,
and
right,
what are the interpretation we can get from these.
right. Yeah. So what I would suggest is if you have a Fortran code ready from which you actually extracted the data, just reverse the code, and then I mean just reverse in the
Reverse
sense.
the
It might
process.
take some
Yeah,
time. Like it might take, like we have the code, we just can prepare, we can read, write, but it might take some time, and we don't.
yeah. Or if you have some mask file for Australia and that region,
That's what I do have.
You
yeah, you
have.
can just mask those oceanic points, and then you can create the same data with this mask file, and using the same mask file, you can just rearrange the data in this phase
Yeah,
composite data.
we'll do that, because we have done. We just read this code and use the mask file and reverse the code, and then
Yeah,
so that may take at least an hour for us to prepare the code. Once the
yeah,
code is ready, we can play with these
The
things.
data. Yeah.
At present, what we have learned is how to use those codes and what are the numbers that we need to supply to them,
right.
and also the importance of this figure, that these first two modes, which are more than 100 number of days, mm, we need to find a reason why they are not.
Yeah, I need to look into the structure of that. I
Right.
mean, I guess that is because of a trend within that particular year. I mean, from the onset to the date of demise, it might have shown some increasing values, and then it actually dropped to the demise value.
Okay.
Right.
I think
So,
so. When I have to look.
so Yeah. So at present, so this code is almost ready. Just we have to write few more rearranging programs and then run it. So what we can do is, John, we can prepare a shell script where we write the first code, and then we can include this part, and then another code we can write as a Fortran code to read the phase composites, and in that same code we can write a plotting. So everything will be done
When,
simultaneously. Another
yeah,
question is,
Yeah.
like, this is done for 1 year, right? And when we say phase composites, it's a combination of all the years, correct?
No, it is just
no,
for
it's
1 year.
the one. It's the phase composites for 1 year,
1 year.
but we
You're
would
just
have to.
working with all. I mean, just 1 year. Yeah.
So can we say like climatology of phase composite by adding all those years composites?
Yeah, I mean, once you have 114 years of data, phase composites, you can just average them, because now when you do a phase composite, it's all basically, the time sense is gone. It's just basically you're
Right.
dividing the phase plane into 8 particular phases, and then you are averaging it.
So
So
can we add all those years, because they
yeah,
might
yeah, you can
belongs to
definitely
different
add. You can
period.
definitely add all, and then average out 114 years to get a smoother phase composite diagrams. And
Okay.
I must say, I mean, phase composite diagrams for each year will look somewhat different, but I mean, the main feature, I mean, if there is a southward propagation of
The main
oscillations, then
features will be
yeah,
similar.
that will be the similar.
Right.
Okay, then Nirupam, we'll work on it, and
Yeah.
Yeah, yeah. Just let me know if you get some figure, and then we'll carry out
And we
discussion.
can discuss.
Yeah.
okay,
Okay.
John, you have some work to do. You just need to save and regrid it. And what I will do, I will also prepare another code, uh, which combine all these codes, and by year we can plot uh,
Right. Do you
these.
want to regroup in another Zoom meeting for that, or do
You
you
want
want
to
to work independently?
discuss it now, or we can?
Yeah, we can discuss it now if you want, if you have time.
Actually, I have to do some work, so we can meet at 5 p.m. today. What do you say?
That may not work because I may have dinner arrangements.
Okay, so any other time today?
I will send you an email and I'll let you know.
Okay, I'll find if it is an evening time. I can sit for few minutes and then we can make it.
Okay, no worries. In the meantime, I'll try to work on code that can rearrange that
Okay.
data, that directory. Could you send me that just so that I could grab that code that you just rewrote and with the phase composite
Yes.
data?
This is the path. You can note it down.
Okay, let me just write that down
And
real
let me
quick.
stop recording. I'm not sure where it is going.